Okay, so today we're doing limits. And here's the deal. Limits are basically the foundation for all of calculus. Derivatives, built on limits. Integrals, built on limits. If you get this one idea, and you will, the rest of calculus is just using it over and over. So let's figure out what a limit actually is. And I want to start in your car. Your speedometer says 60. Now let me ask you something. Are you going to drive 60 miles an hour for an entire hour? No, you've got a red light coming up. In 10 seconds, you'll be at zero. So that 60 isn't a promise about your next hour. It's measuring something about right now. Okay, so think about what that would take. What is speed? Distance over time. How far you went, how long it took, divide. Cool. How far do you travel in one single instant? Zero. How long does an instant last? Zero. So the speed right now is zero over zero. Can you divide by zero? No, you cannot. Do you see the problem? The only recipe we have for speed just died at exactly the moment we care about. So here's what we're going to do about it, and honestly, this is the whole game. If you can't measure at the instant, measure around it. Take the 1 second wrapped around that instant. In that second, the car went 88 feet, and 88 feet per second is 60 miles an hour. Done. Not quite, and you already know why. Your foot was easing off the gas during that second, so what you measured is a little bit of a blend. A little faster at the start, a little slower at the end. Fine, shrink the window. A tenth of a second, better, still a blend, a hundredth, even better. Every window still blends a tiny bit of speeding up or slowing down into the answer, so every answer is still a tiny bit off. That never stops being true, by the way. You can shrink forever and never get a perfect one. Are we stuck? No, this is where the idea shows up. Stop looking at any one answer and look at all of them together. The way I like to think about it, each measurement is a guess and the guesses are settling down. Watch them land. Every time the window shrinks, the new guess moves less than the one before. They're clustering, like shots tightening around a bullseye. They are trying to reach one specific number, and they never need to arrive because you can already see exactly where they're headed. That number, the one the guesses are trying to reach, is called the limit. And for your speedometer, that number is 60. The thing on your dash is a limit, computed live, every moment you drive. Now let's run the same game somewhere we can hold everything still. Here's a function. It's a fraction, 2 minus 2x squared on top, x minus 1 on the bottom. Graph it, and it's basically the most boring graph in the world, a straight line. Except plug in x equals 1, top 0, bottom 0, 0 over 0, and we just talked about that. No answer. This function has no value at x equals 1. There's a hole in the graph, an actual hole, one missing point in an otherwise perfect line. But check this out. Put your finger on the line. That yellow point, that's your finger. Slide it toward x equals 1 and ask, what height is my finger trying to reach? You can see it. The line is aiming at one exact spot. Slide in from the other side. Same spot. The function says nothing at 1, and it doesn't matter because everything around 1 is pointing at the answer. Your finger is trying to reach minus 4. So the limit of this function, as x approaches 1, is minus 4. There's how we write it. And all that notation says is, as x gets really, really, really close to 1, the outputs get really, really, really close to minus 4. That's math speak, by the way. Really, really, really close is a technical term. Mathematicians write approaches because it looks better in a textbook. Now here comes the part where everybody trips at least once, so let's go a little bit slowly. The value at a point and the limit at a point are two different questions. Watch three functions. Near x equals 1 they're identical, same line, aiming at the same spot. At x equals 1, three totally different stories. First one, whole, no value. Second one, somebody pulled the point out and stuck it up at 2, wrong spot. Third one, filled in right where you'd expect minus 4. Ask them for their value at 1, nothing, 2 minus 4, three different answers. Ask them for their limit at 1, minus 4, minus 4, minus 4. Same answer 3 times. Now notice what I'm not saying. I'm not saying the value doesn't exist or that values don't matter. The second function has a perfectly good value at 1. It's just sitting in a silly place. What I'm saying is the limit never looked at the point. Not once. In plain English, the value is what the function does at the point. The limit is where the neighborhood says the function is trying to go. Different questions, sometimes different answers. You feel okay with that? And here's why you should actually care about that difference, because right now it might look like a technicality. Go back to your car. At that instant, what was the value of your speed? 0 over 0. There wasn't one. No value at all, but there was a limit, and that limit is the number your dashboard shows you. That's the entire business model of calculus. It operates at exactly the points where plugging in fails. When we build derivatives a few videos from now, every single one starts life as 0 over 0 and gets rescued by a limit. The same move every time. And if you're headed toward engineering, this distinction is your whole professional life. No instrument measures at a point. A sensor samples a tiny window around an instant, something like 1,000th of a second. So every reading an instrument ever hands you is one of those window guesses from the car, and the limit is the number the guesses are chasing. The value at a point is one report. The neighborhood is the evidence. Fair warning though, sometimes the guesses aren't trying to reach anything. Here's cosine of pi over t as t heads toward 0. From out here it's a wave, no big deal. Zoom in and it wiggles faster. Zoom again, faster still. Inside any window around 0, take one as thin as you want, something like a millionth wide. This thing still swings all the way from 1 down to -1. Run our game on it. The guesses go 1, -1, 1, -1 forever. They aren't clustering. The bullseye is just empty. So the limit does not exist, and hear that as a real answer, not a shrug. The function honestly has no destination there, and now you know that about it. One more thing, because this will absolutely show up in your homework. Our whole game is, take some measurements, watch what they're trying to reach. So how many measurements until you can trust it? Check this out, I'm going to cheat. Same wild function, but I choose the sample points, and I choose them dirty. Only the spots where the wave bounces back up to the same height. Look at the table, every value identical. Settled, right? It's a lie. Between my hand-picked points, the function is going absolutely nuts. So a table can hint at a limit, a table can never prove one. Proof means computing the thing for real, and that's a skill we build 2 videos from now. Okay, let's wrap it up. What is a limit? It's the number the outputs are trying to reach as the input closes in. That's it, your speedometer, a limit live every second. The hole in the graph, no value, perfectly good limit because the neighborhood outvotes the point every time. The wild wave, no limit, and that's a real answer. And next time, a puzzle. A function where the left side is trying to reach one number and the right side is trying to reach a different one. What should the limit be? Think about it before you watch. You feel okay with limits. Good deal, that's the video.